So we spent a ton of time already working with exponents when we went through radicals and roots, but now we want to talk about the exponential function. So up to this point, we've kind of worked with the base of something being our variable, and then our exponent was a constant. When we talk about the exponential function with base b, now we're going to have a constant raised to the variable. So the exponent is what's changing, and hence it's an exponential function. The one stipulation we want on this base, though, is we don't want negative numbers because that would be really difficult to kind of work with, and it's not always defined. And we also don't want 0 as a base, and also 1 as a base is really boring. So we have some just extra stipulations on what that base needs to be. So before we actually begin with just the generic graphs of each of these, we're going to start by graphing two exponential functions just by plugging in values for x and finding the corresponding y. So we'll begin with graphing 2 to the x. So for the very first one, if I plug in x equals 2, my y value will be 2 squared, which is 4. So our graph goes through the point 2, 4. When we plug in 1 for x, 2 to the first power is 2, so we go through the point 1, 2. When we plug in 0, 2 to the 0 is 1, so we go through the graph here. Now remember back to our exponent rules. If we have a negative exponent, we need to change its position to make it positive. So for this, when I plug in -1 for x, I would flip its position to give us 1 over 2 to the first, or 1/2. So when our x is -1, our y value is 1/2, which is roughly about here. Same thing, when I have -2 in the exponent, I flip and move it to the bottom, and 2 squared is 4. So when I plug in -2 for x, my y value is positive 1/4, which is right around here. So you can pick more points if you want, but we get a decent picture for this exponential function, y equals 2 to the x. Now if we change this base to 1/2, instead we're going to see kind of an opposite effect. So when I take 1/2 and squaring it, remember we can distribute that square across division. So this is 1 squared over 2 squared, which leads us to 1/4. So when x is 2, our y value is 1/4. When we plug in 1, that just means 1/2 times itself once. So this is going to be 1/2. So our y value is roughly about here. When we take 1/2 to the 0, that still equals 1. So we go through this point. And now when we plug in negative numbers, we distribute that still. So this is 1 to the -1 over 2 to the -1. And we have to flip both of these to make them positive. So it becomes 2 to the first over 1 to the first, which is really 2 divided by 1. So I'm having the opposite effect when I plug in negative numbers. This is when I'm getting something big. And then the same thing when we plug in -2 as the exponent. This would be 1 to the -2 over 2 to the -2, which flips. So it's 2 squared over 1 squared, which gives us 4. So we end up through this point, and our graph really is just flipped. So this is our graph of 1/2 to the x, okay? So just so you can see, if we put these on the same graph, they are reflections about the line y equals x. So in general, really the base is going to dictate what the shape of the graph looks like. If your base is a number that's bigger than 1, so this would be something like y equals 2 to the x, 3 to the x, 4.9 to the x, doesn't really matter. That base is something bigger than 1. You're going to go through the point 0, 1, because anything to the 0 power is going to be 1. And then you're going to have that same shape as our last graph. So it will look something like this. Okay. When we plug in a negative number, it's still going to go through the point, or when we plug in a base between 0 and 1, still going to go through the point 0, 1, but it's going to go in the opposite direction. So it's going to look more like this, okay? So the base tells us what the shape looks like. In both of these cases, we hug the x-axis, which is that line y equals 0. Okay? So all of the properties for these are the same. It's just one graph is a flipped version of the other. So the domain, you can plug in whatever you want. The range will be 0 to infinity. You can't actually equal 0. We have no x-intercept, but we do have a y-intercept of 0, 1. There is no vertical asymptote, but we do have a horizontal, which is y equals 0 or the x-axis. Okay, so if you know the base, you know the shape, and we can apply all those transformations to it. So there is one specific base that we're going to be working with a ton, which is called our natural base. So the natural base is just a very specific number, and it's kind of like pi. Pi is something that just kept appearing over and over, so we gave it a special symbol, but it's just a number. It's 3.14159, keeps going on forever. Our natural base is a number that's called e. And so e is roughly about 2.718. So when we deal with plotting e to the x, its base is bigger than 1, so it still goes through 1, 0, and it has that same shape as a base bigger than 1. Okay, so let's go ahead and let's get some practice with our transformations again. We're going to graph the exponential function, and then we're going to state the domain, range, and horizontal asymptote. So when we look at this function, if we ignore all of the constants, I'm going to rearrange it. We're starting with a graph of y equals e to the x. And then we really have two different transformations here. We have this plus 2 on the outside, which tells us we're moving it up 2. And then we have this minus sign. It's not attached to the x, so this means we reflect over the x. Okay. So those are the two transformations. We always do the vertical last. So the first thing we need to do is the reflection. And the second thing we need to do is then shift it up 2. Okay. So you can draw a couple graphs in here if you need to. I'm just going to do 2 of them for the two transformations. And then we can find all of the important pieces because we have our starting graph right up here. So very first thing I need to do is I need to take that graph and I need to reflect it over the x-axis. So we usually go through 0, 1. Now we're going to go through -1. So our point will be down here, and then it has this shape. So this would be the graph of just negative e to the x. And we're going to have to state our horizontal asymptote, so I'm also going to keep track of that, which is still going to be y equals 0. Now I'm going to take this graph and I'm going to move it up 2. So here's -1, here's +1, here's 2. So when I take this and I move it up 2, my new horizontal asymptote is up here at y equals 2. And then our point here would move up 1, 2 to +1. So we will go through +1. And then our graph will still have that same basic shape. So here's the graph of 2 minus e to the x. So using this graph, we now can find the domain, the range, and then the horizontal asymptote. Domain is not changed at all. You can still plug in whatever you want. Your range, however, is everything up to 2. So in interval notation, that would be -infinity to 2. And then our horizontal asymptote has moved to y equals 2. Okay. So one of our main components of this unit is we're going to be solving a lot of exponential and also logarithmic equations. And we're going to use this property of 1-to-1 to help us out a lot. So if I have b to the x equals b to the y, That base, remember, is just a constant, so the only way this can happen is if these two exponents are equal to each other. So when I'm trying to solve a log or exponential equation, I want to try to write them with the same base and then set those exponents equal. If I can't do that, I'm going to have to do something else, which we'll see in the future. But your whole goal is to write everything with the same base, set the exponents equal. So in this first example, I have 7 to the x, my base is 7. That means I want to write this side with a 7 to a power as well. So 49 we can rewrite as 7 to the second. Okay? But I don't have 7 to a power equals 7 to a power, so I've got to do more manipulation with this side. Okay? That being said, remember we can always change the position, and all that does is change the exponent. So 1 over 7 squared is exactly the same thing as 7 to the negative 2. And now here I have 7 to a power equals 7 to a power. It means these exponents must be equal. So from this we get x equals negative 2. And so this is our value that solves this equation. And you can plug it back in, verify that it does work. But we've figured out what x needs to equal to make this a true statement. Okay? So for the second example, we want to try to do exactly the same thing. We have 5 to a power. We hopefully can write this 125 as 5 to a power. And thankfully we can. 125 is the same thing as 5 to the third. And now because they have the same base, we can go ahead and say these exponents need to equal each other. So we need to figure out, where does 2x minus 3 equal 3? So we just solve for x by adding 3 to both sides. That gives us 2x equals 6. And then we divide both sides by 2. And this tells us our x value needs to equal 3. So this is the x that solves this equation. Right? So we're going to get more complicated ones in the future, but for now, you at least want to try to write everything with the same base. Now the other nice thing that happens as a result of these exponentials is we can talk about many different applications. So they have a lot of applications in biology. So if you have to take any kind of those classes, you'll kind of talk about bacteria growth. So if you think of like a cell, it splits and you have 2 cells now, each of those split, and you would have 4 cells. Each of those split, you have 8, then it splits again to 16. That's really an exponential function 2 to the x to represent that bacteria doubling. The other major application is going to come in the form of interest. So we have 2 different types of interest, compound interest and then continuously compounded interest. So compound interest is going to be something like a loan, or if you have a credit card, you have some kind of percentage rate. You can also earn interest if you have a savings account or you put money in like a mutual fund. You can get some kind of rate on there. And then continuous compounded interest is something that the number of times it's compounded is basically infinite. So the best example you can kind of think of, or the closest realistic example, is if you ever look at your credit card statement, you have something that's called a cash advance. So you can look or you can take out money at an ATM using your credit card, but the second you take it out is when you start accruing interest. And then from there, that interest is just going to grow very, very, very rapidly until you pay all of the money back. So it's rare you're going to find an account that works in favor for you. So the first one is the one we're going to see more typically. And we just have a straight formula. Our A is equal to P times 1 plus R over N to the NT. The continuous compounded interest is a simpler formula to remember, A per. A equals P e to the RT. So in both of these, the variables mean the same thing. This value of P is called our principal. So it's basically the amount of money you invest in the account or the amount of money you borrow from the account. This value of R is the interest rate. Okay, so you want to make sure you always enter that as a decimal. So say you have a 5% interest, you would enter that as 0.05. T in both of these equations is time, so it's the amount of years that your money is invested. And then N is unique to just this first equation. It's the number of times per year the interest is compounded. So to give you some examples, if you have monthly, then your value of N is 12. If you have daily, then your value of N is 365. If you have weekly, there are 52 weeks in the year, so your value of N is 52. Okay. And then last but not least, the value of A is just the amount in your account. Okay. This value of E, remember E is just a number, it is that base, it's about 2.718. So you have that button in your credit card. So let's just try one quick example. We decide to invest $30,000 in a mutual fund earning 4% interest per year. How much money is the investment worth in 3 years if the interest is compounded monthly? So I'm going to refresh on our formula. Our amount is P times 1 plus R over N to the NT. And we just have to figure out what each of these values is. So P is that principal. It's the amount of money we invest. So our value of P is 30,000. R is the interest rate, which is 4%, which as a decimal is 0.04. Okay. Then we need T, which we're told we're putting this money in here for 3 years, so T is 3. And then last but not least, we need our value of N. This interest is compounded monthly, so N is equal to 12. So from here, it's really just a plug and chug in our formula. Our amount that will be in the account is equal to 30,000 times 1 plus our rate, which is 0.04, divided by the number of times it's compounded, raised to the NT. So give this a try. You can plug this into your calculator. Definitely get used to your handheld though for your exams. This should give you roughly about $33,818.16. And it's money. Anytime you're dealing with money, you round to the nearest penny.